Okay, so today we want actually to start a new chapter. This is if you go to the book you're following in the book, that would be chapter 17. Chapter 16, we covered most of it, especially when we talk about capacitors and the energy stored in capacitors, charge, etc., combination of capacitors. In this chapter, chapter 17, we want to talk about current, resistance and current, and Ohm's law specifically. So let's see what that means. Remember, we started in the previous chapter, and even before that, we talked about a perfect conductor, a perfect piece of conductor, where actually the electrons or the charges are completely free to move. So they don't require any potential difference at all. But actually, in real life, nothing is perfect. So what we're going to consider is now a piece of a non-perfect conductor, or a imperfect, right? I think imperfect is a word. I don't know. Or you want a semiconductor. What I'm gonna do is I'm gonna take this piece of conductor, and I'm gonna connect it to the battery. So I'm gonna connect one side to the negative pole of the battery, and the other side to the positive pole of the battery. Now there's going to be a voltage difference across this piece. How the wires that I'm considering here, I assume that these pieces are perfect conductors to see what's going to happen inside this specific part. Now there's a voltage difference. Vp is larger than Vn. So there's going to be an electric field pointing from the high voltage to the low voltage. Now, if the charges inside the conductor are electrons, these electrons are going to feel a force. And this force is going to be opposite to the direction of the electric field. Now, even though this material is not a perfect conductor, but the electrons still can move. So they're going to have an acceleration and velocity in the direction of the force applied on them. So there would be electrons flowing in this direction. طبعا الالكترونز don't actually have a very long free path، هي بنسميها انه ده في مسافه فيهم يمشوا. ليه؟ because what's going to happen inside the conductor, these electrons are going to collide with the nuclei, with other electrons, so they're going to get close to the protons, they're going to be attracted to them, so they're going to be stuck. But what happens is some electrons move from here to here, then another electron moves from here to here, and another electron moves from here to here. So we have a flow of charge, a net flow of charge in a certain direction. Now, electrons are negatively charged, so we can imagine that there is a positive charge flowing in this direction. Now, the flow of charge, we call it a current. And how do we define it? The current, we define it. If we take any cross section inside this wire and we start counting how much charge passes us in a certain time interval. So I take a stopwatch, بعير أنا مثلا 1 second, 5 seconds, whatever, and I count in this 5 seconds how much charge flow through. يعني قد ايه بيمرق charge من ميله لميله through this yellow surface. The rate at which the charge is flowing, I call that the intensity of the current, or simply current. So I give it the symbol I, and I measure it in the standard unit ampere. And I is equal to dq over dt. Now, because the flow of charge has to be continuous, if I measure the flow of charge here, and I measure it here, or I measure it here, it has to be the same. So there would be no accumulation of charge. So it's just a flow. The charge بيظهر من ميلي بيرجع بيجي من ميلي تاني. So it is a flow of charge. Of course, in this formula, dq is measured in coulomb, and dt is in seconds. So ampere is 1 coulomb per second. So if we look at the microscopic view of what's happening, as we said, inside the conductor, these electrons are gonna feel a force, but they're gonna start moving. Now, electrons, even though if we don't have an electric field applied, electrons are always moving. So they are moving in a random directions. واحدة طالعة طلوع، واحدة رايحة على اليمين، واحدة رايحة لقدام. And then they collide with the atoms or get close to the atoms, and then they turn around, they move back and forth. But there is no net flow of the charges. Now, when we apply the electric field, now the electrons still move around. They're still moving randomly all around. But as they move, they drift forward. يعني كنت تتخيلوا صف روضة أولى قاعدين بالصف عم يلعبوا، كلهم عم يمشوا يمين شمال قدام ولورا طلوع نزول على الطبقات، بس they are staying in the same position. But now إذا المعلمة عم بتمشيهم، هنهم عم بيمشوا مع المعلمة، بعدهم عم بيمشوا يمين شمال، بس in total they are drifting in a certain direction. يعني هن عم بيمشوا بالصف، بس الصف مش صف جالس مثل صف العسكر، صف وعم بيزيحوا يمين شمال ولقدام ولورا، واحد بيدوبل عن الثاني. So that's basically what the electrons are doing inside. Now, what I do is I call the average velocity in the direction of the current the drift speed. It's not magnitude. It's not direction. It's magnitude only. So I call it the drift average speed. So the electrons has an average speed. We call it the drift speed. Now, if I take a cross section of the wire, this cross section has an area of pi r squared. Now, I take also a stopwatch. أنا قلنا شو هي الكارنت؟ هي time a charge that passes a certain point over a certain time. So أنا عامل الكاونتر تبعي هون. So I put my counter here. I take a time interval delta t. So I take a time interval delta t. It could be 1 second, 2 seconds, 10 seconds, whatever. I'm going to divide by it at the end. And then I start counting how many electron passes. Now, the electrons that are going to pass this checkpoint are the electrons that originally, when I started my stopwatch, were close enough for their drift velocity to take them across the line. يعني نرجع للاكزامبل تبع المدرسه. انا عم نعمل امتحان. I announce انه بعد عندكم 5 minutes لتخلصوا الامتحان لتسلموا المسابقه. الناس اللي رح يخلصوا الامتحان اللي رح يوصلوا للفينش لاين هن اللي كانوا already خلصوا enough او close enough to the finish line to pass it. طيب قد ايه لازم هالفينش لاين؟ قد ايه بده يكونوا close enough؟ لازم يكونوا within an interval length of v drift times delta t. كل الموجود in this area اللي هو طوله v drift times delta t they would pass. So all the electrons that were here, or the free electrons of course, that were here are going to be passing, and they would contribute to dq. So dq is equal to the charge of the carrier, the charge of the electron, times the number of electrons that are going to pass. But the number of electrons that are going to pass are equal to this volume here that I have, times what I call the charge or the carrier charge density, or the carrier density. يعني هودي الاريا من هالفوليوم سوري من شو معمول من اتومز. اذا كنت مثلا عم بحكي عن ايرون، كل ايرون عندها 2 free electrons to move. اذا كنت عم بحكي عن كوبر, I think copper has 1 per atom or 2. So different material have different number of electrons that they contribute. So حسب الفوليوم، حسب كيف هالاتومز they are oriented بيكون عندي تشارجز. احنا قلنا كل التشارجز، مش كل التشارجز طبعا، كل الفري تشارجز، لانه التشارجز that can move هن مش كل الالكترونز ولا البروتونز. البروتونز are completely stuck in the nucleus. والالكترونز حتى الالكترونز القراب للنيوكليوس they are stuck. Only the electrons that are in the outermost shell, if you remember your chemistry, are the electrons that kind of free to move. They can form these conductive electrons, I call them. So n, the small n, هي density of these free particles. So n number of charges that are gonna pass in this time interval هي التشارج density times whatever مش charge density carrier density whatever volume that I assume that contain these charges that are going to pass. الفوليوم هو length that I was talking about اللي هو VD times delta T بهالتايم انترفال تبعي multiplied by the cross sectional area اللي هي pi r squared. انا عم باخذ فوليوم هيدا الواير تبعي so it has a certain volume so يمكن كان نكون عم نحكي انا في خط هون في خط هون في خط هون في خط هون all those are carrying charges so the bigger the area is the more lines I can allow these students to flow through اذا بدكم هذا الباب عندي so صار انا عم بوسع الباب صار عم يمرقوا اسرع هالالكترون so that's basically what is the area والlength هي شو هي قد ايه سرعتهم لهالناس ضرب قد ايه انا عم بعطيهم وقت so اذا واحد بعيد عني مثلا متر وسرعته 1 متر بير سكند وانا اعطيته 1 سكند بيوصل بس اذا بعيد مترين ما بيعود يوصل so it's just the interval that these have enough time to pass my door in this time interval so the Q delta Q هي QC times N the charge لكل كارير ضرب عددهم وعددهم هو density times الفوليوم والفوليوم هي length times area والlength هي شو هي ال V drift times the time I give them so now when I find I which is dq over dt the dt cancels out and I have q n a times V drift so the current is related to the charge of each carrier يعني هالبارتكلز اللي عم بيحملوا تشارج قد ايه كل وحده التشارج تبعها اذا كانوا الكترونز بعرف التشارج انا لكل الكترون times their density how common they are how many charges I have free times the thickness of the wire how thick the wire is how big the door is times how fast they are drifting not how fast they are moving because they are moving randomly basically but they are drifting in the direction of the current so that's basically what the current is so it is how much charge or the rate at which charges passes so basically it is the how common the charge carriers are so we need something to carry the charge times the charge that each of these carriers carry times how wide the area they are moving in اذا بدنا نتخيلها مثل النهر قد ايه عرضه لهالنهر and how fast the drift of these electrons is moving now as we said this is not the complete motion of the electrons there's something I call the free path of electrons the free path of electrons is how much an electron moves before actually it changes its direction randomly due to interacting with something else so basically when we apply an electric field in this direction the electrons are going to move in this direction but you see how the electron moves it moves this way it hits something it moves this way it goes back it moves this way up down so the distance the average distance that it moves without hitting something without changing direction is called the free path of the electron and that's usually depend on the material now this free path it's a fundamental quantity. I can look at the microscopic level and find this free path. But if I'm doing electronics, I don't care about each electron alone. I want to look at the total flow rate. I want to look at the total charge, the current that is flowing through the circuit, and relate that to the voltage that I am applying on this piece of material, the voltage difference between points A and B. So this hindrance of motion, I can characterize it, but what I call the resistance of the material or this semiconductor piece. And the resistance kind of group all these kind of interactions that these particles have inside. And it relate for us the voltage and the current through the resistance. So the current depends on the material resistance as well as on the applied potential difference. So I can write this empirical equation, if you want, that the current that I have flowing in this piece of material, this is a mistake, huh? Let's fix it. So I already posted this file for you, so please fix. It's delta V over R. So it is how much I push the charges by this potential difference over the resistance of the material. Now, the resistance of the material can depend on a lot of things, on the shape of the material, on what it's made of, and it might actually depend on delta V itself. So devices that their resistance is constant, do not depend on delta V, are called ohmic devices, of course, related to Ohm's law. So these devices, when I apply a voltage on them, the current depend on the voltage. And we got voltage or delta V function of I as a straight line. But if the resistance itself depend on the voltage, I'm not going to get a straight line. I'm going to get a complicated figure. For example, a diode would have a very large resistance if the voltage is negative, and it would have a low resistance if the voltage is positive. So when the voltage is negative, the current is almost zero. But when the voltage becomes positive, it becomes a conductor and we have current through it. So the resistance is measured in the unit ohm, again, after the scientist ohm. And it's basically 1 ohm is 1 volt per ampere. So I'm defining an empirical quantity that relate the current, how fast the charge is moving inside my conductor, to the potential difference or the voltage difference that I'm applying on this conductor. In this chapter, actually, we're going to focus on ohmic devices, on devices that obeys Ohm's law. هلا مثلا في طلع انا الكاباستر منه اوميك ديفايس بيمشي شوي التشارج وبيوقف. So it would have an infinite resistance after a short time لما يصير الكاباستر charged. الاوميك devices هن basically كل الميتالز are ohmic devices. They have a certain resistance. So let's see the resistance of these materials, the ohmic devices materials. What does it depend on? Right. أول شيء, it would depend on the shape of this conductor or semiconductor. So if we have a wire and I apply a voltage difference here on the total, so I point A here and point B here. Now the current has to flow from so if VA أكبر من VB, the current has to flow in this direction. Electrons بيمشوا بالعكس. الcurrent هو, I call it for the positive charge, so it moves from A to B. So here VA larger than VB. So the longer the wire is, the more obstacles these charges that are moving have to overcome. So the resistance of this piece depend on its length. And when I say length, it's the distance that I have to move from where I'm applying the voltage in the direction of the current. But also, if I increase the area of the material, the cross-sectional area, so how wide this material is. So if I make it wider or narrower, if I make it wider, I have more charge now that can move. Remember, I depends on A, the cross-sectional area. So the resistance decrease with the cross-sectional area. So I have more charge that can carry, or more carrier that can carry my charge around. So I kind of flow in that direction much easier. So R is inversely proportional to A. Finally, if we remember about the current, it depends on these two terms اللي هن small n charge carrier density and the drift velocity. and the drift velocity قلنا بتعتمد على الفري باث وما بعرف شو. so بتعتمد على الماتيريال من شو معموله. how good of a conductor this material is. اذا كنت عاملها من كوبر غير ما اكون عاملها من جرافايت انا. so this material all these I group them in what I call the resistivity of the material rho. So I give it the symbol rho, the Greek letter for R. It looks like a P in English, but it's actually pronounced R, so it has the R sound. So the resistivity of the material. So I can put all these together, and I can say that if I have a conductor or a semiconductor, that of course is an ohmic device, its resistance is equal to rho L over A, where rho is the resistivity of the material, it's property of the material. It doesn't depend on the shape or whatever. مثل density. density للwater for example ما بيعتمد قد ايه عندي انا كبايه مي ولا خزان مي. نفس الشيء هون. بس الريزيستنس بيعتمد كمان على الشيب، على الطول والكروس سكشن. So R equal rho L over A. Now, in terms of the unit, L in meter, A is in meter squared. Rho, sorry, R is in ohm. So rho لازم تكون ohm meter. You can look here in the table. You can see different materials have different resistivity. So silver has the resistivity rho 10 power minus 8, copper 10 power minus 8, gold 10 power minus 8, aluminium 10 power minus 8. Again, so these are the metals, these are the conductors. They have very low resistivity. That's why when we are use them with something else, we can ignore their resistance because they have low resistivity. If you go to the semiconductors, مثلا carbon لما تكون بالجرافايت, it's still a conductor. It's 10 power minus 5. But we have silicon, germanium. But if we go to insulators, this number jumps very high. So resistivity of glass is 10 power 14. So it's a complete insulator. So it has, compared to silver, for example, it is infinite resistivity. Now, resistivity itself actually depends on temperature. And as we increase the temperature, some materials actually becomes more resistive, some materials becomes less resistive. So they have this coefficient, the temperature coefficient. And if I know their resistivity rho 0 at temperature T0, I can find the resistivity rho at temperature T by applying this formula. If alpha is positive, then the resistance increase with temperature. If alpha is negative, then the resistance decrease with temperature. So see, the metals have positive alpha, but the semiconductors have negative alpha. In circuits, actually, we use resistors a lot. Of course, we use resistors in a larger scale, for example, to heat things. So because they are slowing down the current, they are taking some of the energy, the electric energy that I give from the battery, and they actually change it to heat. So we use those to heat water, like بالأذان, بالسخان المي, all الدفاية. So we can use them for heating. But in electric circuits, we use them to control. So we have all these different resistors that we can use them to control the current in the circuit. And of course, the current basically is the signal. So we can use them with capacitors and other stuff to control our circuits. There are some resistors in circuits, we can use them as variable resistors. So they have a knob that we can change actually the resistance. We call those rheostats. If we go back to the lab, we will see them together. This we'll talk about it in the lab. Before we come to combination of resistors, let's do some problems together. Do I have them solved here? I think so, yes. on a combination. Okay, I have other problems. Let me find them. Or we can just get them from the book and solve them again together. I have to decide on the midterms, but I'm thinking after the break, right?
Yes, please.
بس ما المشكلة إنه كلها حيعملوا لكم after the break, so pay attention.
لا أنا I already have to قبل البريك.
دكتور يومين بعد
على
العشرة
10 فينا نعملهم ب9 أو ب7. لحظة شوي، عيد الميلاد الأرمن ب9 ولا ب8؟
6.
6. اوكي. 9 ولا
دكتور
ب8؟
مش أفضل المواد اللي مش اختصاص تنعمل قبل العطلة، لأنه على الأغلب مواد الاختصاص كلها تكون بعد العطلة، فهيك بنقسمهم يعني مواد الاختصاص هي اللي فيها تقل أكتر.
لا مش
المشكلة إنه أنا
إجباري.
I have to choose the same
100%
date
بيكون
for
ممتاز
1
هناك.
and 10 حتى ما أروح من مشوارين على الجامعة.
خلاص نمشي نعملهم كلهم قبل العطلة ونرتاح فيها للعطلة.
بدنا علامات.
طيب خليني أفكر فيها أنا، لأنه بدي أخلص كمان التشابتر حتى نكون في عنا enough material to cover بالإكزام.
هلا دكتور
مشكلة
أنت رح
دكتور،
تعمل
مش مشكلة.
لنا سامري أو شيء؟
سوري؟
سامبل رح تعمل لنا سامبل، تعطينا سامبل مثل الإكزام أو شيء، أو
يا
بس رح
شور
تقول
قبل
لنا
ما
بس
نوصل
ممكن؟
للإكزام نعمل سامبل ونحل extra problems.
اوكي.
طيب let's go back to our problems. Where is it? Okay. Back to sharing. طيب these are from the book. A resistance of 100 meter long copper wire with diameter 2 millimeter is how much? So I have a copper wire, length about 100 meter. So the current is going to flow in that direction. And I have the thickness or the diameter of the wire is 2 millimeter. Now, resistance is equal to rho L A. The wire is made of copper, so I have to copy the resistance of copper. So I copy that from the table that I had in the previous slide. So 1.69 times 10 power 8 ohm meter. Now I have to find the cross-sectional area, this area. Now, when they give me a diameter, it means that the wire is cylindrical, so the area is a circle. So the area of the circle is pi r squared or pi d squared over 4. Of course, I have to change d to meter. Pay attention to the unit. I got A is pi times 10 power 6 meter square. Now, the length is 100 meter. So I apply that. So I have 1.6 times 10 power minus 8 over this area multiplied by 100 meters. I got 0.54 ohm. So that's the resistance of a very long copper wire. It has a 100-meter length. طيب. What resistor would you have a current of 1.5 milliampere when connected across a 1.5 volt battery? So when they give us the 1.5 volt battery, so that's the EMF of the battery, or delta V. So I connect the conductor here and here. Now I want the current to be 1.5 milliampere. So the current is going to flow in this direction. I or delta V equal to IR, or I equal to delta V over R. And I want to find R, sorry. So R is delta V over I. So I have to change the current to ampere. So I got 1.5 over 1.5 times 10 power 3. So that's 10 power 3 ohm, or 1 kilo ohm. So to have a current of 1 milliampere, I need actually a large, not very large, a large resistor of 1 kilo ohm. Number 40. You have some copper wire that you want to connect from a power supply to a 150 ohm load. The wire is standard 24 gauge, diameter 0.51 millimeter. What is the maximum length of the wire you can use without its resistance exceeding 1% of the load? احنا قلنا لما نعمل wires, usually we ignore the resistance. We assume that they are perfect wires. طيب, is that logical or not? هذا السؤال basically what it's saying. انا عندي load, عندي هيدا الديفايس مثل هيتر or whatever, resistance تبعها 150. طب انا بدي اوصلها على البطاريه، بدي اوصلها بشريط من هاي الميل على البطاريه، وبدي اوصلها بشريط من هاي الميل على البطاريه. الشريط تعطيني هن الديامتر تبعه. هودي الستاندرد وايرز that come in يعني electricians use. هيدي بسموها ال 24 gauge. You can look up what these gauges are. There's a table for them. كل gauge بيعطوك الديامتر تبع الواير تبعه ومن شو معمول. So قد ايه في استعمل طول هالشريط، شرط انه انا ما اطلع فوق ال 1% من ال 1.5 ohm. So I want my resistance to be 1.5 ohm of this wire. The copper resistance is equal to rho copper times L over A. طب انا الرو copper بعرفها. We find it in the table. I want to find L. Well, A, I find it from where? I find it from the diameter. So as I did before, I use A pi d squared over 4, and that gives me the diameter as the area, the cross-sectional area of the wire. So I can put that back and I find L. So I got L equal to 20 meters. I want to... Okay. So it's shorter than this 100-meter thing. Why? لأنه هون عطيني الديامتر 2 millimeters. هون 0.51. So ربعة. So that makes sense. So I can have a wire of 20 meters without exceeding this 1% of the load. فإذا بطوله أكثر للشريط، طبعا الشريط بيصير عم يصرف انرجي، يعني الفولتج اللي بيوصل على اللود بيصير اقل من الفولتج اللي انا حاطه للباتري. ليه؟ لانه صار في فولتج ديفرنس بلس الكوندكتور. بطلت يعني اذا باخذ نقطتين، شو معناتها البيرفكت كوندكتور زيرو ريزيستنس؟ يعني اذا باخذ انا نقطه هون نقطه هون، هاي بسميها A وهاي بسميها B. VA and VB are equal, so there is no voltage difference. So this here has the same voltage as this, the battery. إذا في resistance or not negligible resistance, then there would be voltage difference. So that's why if you use a very long wire in your connections, you actually have this a little bit difference in voltage. But you see, this is 20 meter. يعني انتوا اذا بدكم توصلوا شو اسمه السخان المي على البيت مش رح توصلوا بشريط اكثر من 20 meters. بس also load هون هو 150 ohm. That's actually a low resistance. طيب, another question. How much time must a 12-volt battery be connected across a 1.5 kilo ohm load to move 1 coulomb of charge through the load, how much energy does the battery provide during that time? So again, I have the 12-volt battery. I connect it to the 150 kilowatt, kilo ohm resistor. I want dq to be 1 coulomb. So I find I first. I is delta V over R. So the current is 8 milliampere, or 8 times 10 power 3 ampere. The time required is dq over I. I want what is that? Okay. So I have 1 over, let's write it here, 1 over 8 times 10 power minus 3، يعني 1000 على 8 يعني بيطلع 125. So I need 125 seconds. So it requires 125 seconds for the time to have 1 coulomb passing. Now, what is the energy? Now, the battery fixes the voltage. مش مثل الكاباستر الفولتج تبعها بيعتمد على التشارج. So the energy that the battery give is dq times delta V. This is the energy that came out of the battery. So that's equal to 12 joules. So that's the total energy that the battery gave us is 12 joules. We can find the power of the battery. هلا بعد ما حكينا عن الباور نحن، بس if you remember what power is the rate of change of energy. So it's delta PE over delta T اللي هو basically what we care about a lot بنحكي عنه كثير هو الوات. how many watts، يعني اذا بنيجي بنحكي بنقول لمبه كم وات، الانفرتر كم وات، all these. So basically it's how much energy it can give us per unit time. So that would be 12 over 125. So that's actually a very low rate of energy delivered. It's 0.1 watt. Approximately 0.1, a little bit less, right? So that's 0.1 watt. If we compare that, for example, to these LED lamps that we have, they are 10 or 15 to 20 watts, right? One more question. This is not actually from the book. There might be a question similar to it in the book, but I couldn't find it when I was writing this. So a wire has a length of L and cross section area A has a resistance R. So أنا مبلش بهذا الواير طوله L لك وينه هذا الواير والاريا تبعيته A والresistance R. Now I want to stretch the wire to double its original length. What happens to the resistance? What is the new resistance in terms of R? So L prime is equal to 2L. Now, sometimes if we are quick, we don't think much about it. We say we doubled L, the resistance is going to be doubled because R is proportional to L. But the thing is, when we stretch a wire, the material has to stay the same material. I didn't bring a new material. I didn't connect it to a new wire. So when I stretch it, the area has to decrease. It has to shrink in area. Now, if this material has a constant density, then the total volume of the wire has to stay the same. So the amount of the material doesn't change. So V prime is equal to V. And the volume is length times area. So L prime times A prime should be equal to L times A. So when I actually double the length, I have to divide the area by 2. So I didn't only increase the length of the wire, I actually shrank its diameter as well. So by doing that, I actually changed the resistance by 4 times. ليه؟ لأنه صار 2L هون وهون صار في عندي A over 2. صارت 4 rho L over A. So the resistance actually is quadrupled. So it's multiplied by 4, not by 2. There is a formula missing. Where is it? So let's copy those first to our own presentation. I want to cover one more thing today اللي هو قبل ما نبلش بال series والparallel connection. اللي هو الانرجي. So I want to talk about energy and power. If we take this circuit again, we similar to this. We have a resistor R, and we connect it to a battery that has an EMF. Now, there would be a current going in the circuit. The current would come out from this direction and goes around. If we take a time interval dt, consider a time interval dt or delta t. During that time interval, there is a charge that goes around. So the charge that goes around in the circuit, dq, is equal to I, the current in the circuit, times delta t. That's the definition of the current, right? So dq, this is the charge that flow from the positive. If I'm talking about positive charge, it goes out of the positive to the negative, or it would be electrons going from the negative to the positive, but it's same meaning. Positive side of the battery to the negative side. During this time interval. Okay, now the battery loses energy during that. Why? Because we have charge going from high potential to low potential. So delta PE is equal, for the battery, is equal to this Q, delta Q, times delta V. So it's V final, Vn, minus V P. So this is equal to Q, or delta Q, or minus delta Q multiplied by the EMF of the battery. Let's write the EMF as this curly E. So it is times the EMF. So the battery lose some of its stored energy. Where does this energy go to? This energy is released as heat in the resistor. So the resistor heats up. So now the energy that is released in the resistor, so energy released as heat, let's call it E. هو للهيت مستعمل نحن الكيو بس لانه صار عندنا كثير كيوز. So let's call it as E. Is actually minus delta P. So this is the released energy. I can take the absolute value if you want. So I can say that it is the absolute value of the change of the potential energy of the battery. Now, I can define the rate at which energy is released. The rate at which energy is released is equal to the power P, or the power, let's say between bracket power, is equal to this, let's take it an absolute value again, delta PE over delta T, this time interval that I considered. So now let's replace these terms here. So we have E, the electromotive force, times delta Q over delta T. So this is equal to, now dq over dt is just basically I. So that's I multiplied by E. E, where is E? Let me copy it and paste it. So the power released by the battery, I'm taking the absolute value, is equal to the EMF of the battery times the current that flows out of the battery. So this is the energy released from the battery. Now we can apply this same thing for the resistor. So for a resistor, now I don't want to use E, I want to use delta V. So I can say the power, let's write it down first, power or rate at which heat is released in the resistor. Actually it's the same. اذا كان في عندي بس resistor واحد موصول على الباتري it's the same. بس لانه I want to be general, so I'm not going to use E, I'm going to use delta V. So the P is equal to delta V, absolute value of delta V. From now on, when we're using delta V, we're talking about absolute value times I. Now, of course, if the device is ohmic, I can still apply Ohm's law, and I can say that delta V is equal to IR, and I can replace that back in the equation above, and I got P for the resistor, or the energy released in the resistor, changed from electric to heat, is equal to I square times R. وطبعا if I want to find the energy, I can reverse this equation. يعني قد ايه انا طلعت energy total. I can say that E is equal to P times the time interval that I had this device on. Now, I want to point one thing. Remember when we found the energy stored inside the capacitor, we got this half Q delta V? The energy that comes out of the battery is Q delta V. Where is the rest of the energy goes? If we are talking about equilibrium, we have to have a real wire in the circuit. And this wire has to lose some of the energy. So actually the battery gives more energy than the capacitor would store, and the rest of the energy has to go in the circuit. If we don't have a wire, actually a good wire, what we're going to have is we're going to have oscillations. So these charges are not going to sit there. It's just going to keep oscillating back and forth in the conductor. So we kind of ignored that when we talked about the energy stored inside the capacitor, but we have to know that some of the energy has to be lost because the battery gives energy as Q delta V. The capacitor only stores half of it, half Q delta V. Okay. I think this is a good point, place to stop. I will update the PowerPoint that I sent on LMS, and we will talk about series and parallel capacitors next time. But before we do that, let me give you a problem that you can solve as part of your participation grade. Since we these days we talk about a lot about UPSs and batteries and solar stuff, so let's talk about that. Okay.
Doctor,
Any questions, any concerns? So I sent this participation grade. It's participation before Tuesday.